Hello, everybody. So today we're going to talk about isotopes. So what's an isotope? Well, an isotope is kind of like ice cream. Well, ice cream would represent maybe a type of atom, it's a type of food, but there's different flavors for that ice cream. And so we can have different flavors of the same type of element. So I think what we're going to do is we're going to maybe go over the example of how carbon would look. So if we take a look, these are three different isotopes that we have for carbon. This one right here is called carbon 12 because it's got the 12 as your top part. And by the way, this is called the isotope form for the element. So if anybody ever asks you to specify the isotope, you would write it in this form. Okay? And so what all these numbers mean is the bottom number represents the atomic number. Top number represents the atomic mass for that element. And when you round it, we call that really the mass number. And so in common terms, this is just called carbon 12. You just name it after the top part, whatever the mass number is. This would be carbon 13, and this would be carbon 14. If you look, they all have the same number of protons in them, and they all actually have the same number of electrons. So they're not drawn on here, but we can just very quickly draw them in here. And because these are all neutral atoms, they're going to end up having 6 total electrons each. And so all of the isotopes will have exactly that same number. But again, what makes them all unique is that some have more neutrons than others do. And in fact, all of these are going to have the same chemical property, but there's a unique property that this guy right here in red has. And so this guy in red is radioactive. Why the heck is it radioactive? Well, the reason why it's radioactive is it's got more stuff in the nucleus than it should normally have. If it has too much stuff in that nucleus, it's going to end up shedding that extra material off. And that extra material leaves that atom at a high rate of speed, and we call that radiation, which, as you know, can be dangerous. Right? So is there a way to predict which elements are going to end up being radioactive or not? Actually, there is. There is a method. You can use something called a stability curve. And that's exactly what this is. This is a stability curve. And so if you take a look, it's got neutrons on the y-axis, protons on the x, which is really the atomic number. If you have a big atom, where are those large atoms going to show up? Well, they're going to show up here in this region. And if you look, it's above the stability curve. So as a result, that atom is going to be radioactive. Okay, so there is a way that you can actually predict which elements are going to be more radioactive than others. But in general, they're usually very large atoms on the periodic table, or they're at least ones that have a lot more neutrons than they do protons. And so where are the larger atoms on the periodic table? Well, of course, they're on the bottom, right? So if you take a look at a periodic table, all these guys actually are radioactive down here. And the reason why they're radioactive again is because they're relatively large atoms. And many of the isotopes of the elements that are on this portion of the periodic table are also radioactive. Not all isotopes, but some of them are. But I believe all of these guys, all of their isotopes are radioactive down here, which is one of the reasons why they were actually pulled out of the body of the periodic table and written down there. Okay, so now we have an idea of what an isotope is. So how do they actually figure out and calculate these numbers down here? Like, for example, iridium, it's got an atomic mass of 192.217. Well, how the heck did they get that? Well, what they're doing is they're averaging all of the different isotopes that exist for iridium. And then, so we're going to go ahead and do carbon, for example, this guy right here, okay, which is 12.0107. We're going to go ahead and figure out how they derive that number, how they figure that out on the periodic table. Okay. So what they do is scientists actually measure. They take a sample out of the environment of the different of a sample of carbon, and then they actually figure out, okay, well, how much of it is carbon 12, how much of it is carbon 13, and how much of it is carbon-14. And so most of the carbon in the world is in the form of carbon-12. So, and let's just say that maybe that represents, let's say 98% of all of the carbon in the world is in the form of carbon-12. And let's say that maybe for this next isotope, carbon-13, let's say that maybe 1.5% of all of the carbon in the world happens to be carbon-13, and let's say that maybe only 0.5% is carbon-14. So not a whole lot of that actually exists out there in the world that's radioactive. So how would you figure it out? Well, you can't just simply take a straight average, because if you take a straight average, and there's two different types of averages, there's a straight and there's a weighted average. Okay? If you take a straight average, that would make the assumption that each of these isotopes has the same value as the other. That would mean that like 33% of all of the carbon in the world is carbon-12, and 33 1/3% would be carbon-13, and 33 1/3% would be carbon-14. And that doesn't really, that's going to, if you take the average of all those, what are you going to get? Yeah, you're going to get this guy right here. You're going to get carbon-13. So you can't do what's called a straight average. Straight averages do not work. However, you're going to do what's called a weighted average. So how do you do a weighted average? Well, let's use this carbon-12 as an example to figure out what it would be. So what we do is we're going to multiply whatever the mass number is by whatever that percentage is. So we're going to go ahead and take 12 and then 13 and then 14 for the mass numbers for all the different types of carbons. And we're going to multiply them by their appropriate percentages that represent what's out there in the environment, what's out there in the real world. So whenever you want to multiply a number by a percentage, really what you're doing is you're multiplying it by a fraction. Well, what fraction are you multiplying it by? Like if that's 98%, that's really like saying 98 out of a total of 100. Well, what does that give you? Well, that gives you 0.98. So if we just take that number 0.98 and you multiply it by 12, that would be like multiplying it by that percentage. So we're going to take 0.98, we're going to multiply that by 12, and then we're going to take the other number over here, which is not 1.5%, but we're going to move it over again, the decimal place, to 0.015, and multiply that. And then for this one, the 0.5 is going to turn into what number then if we move it over two places? 0.005. And so we'll go ahead and do the math on all of those. So if we take 12 and we multiply it by 0.98, it gives us 11.76. Do the same thing for the next one. 13 times 0.015. That's going to give us 0.195. And if we take 14 and we multiply it by 0.005, that gives us 0.07. Now let's add up all those numbers together. So we'll take this one. We're going to add it to the 0.195. And then we're going to add that one to the 11.76. And so what we get is we get a number that is 12.025 AMU. Now again, I approximated these numbers up here. I don't know exactly what they are in the real world, but if you take a look, you can see how you don't get the average of 13 out of those numbers. Instead, you end up getting a number of 12.0215 atomic mass unit, which would be, it's not super close, but it's relatively close to what the periodic table has, which is 12.01. Okay, so again, if I were to look these numbers up, I could probably get them actually closer, but that's not too bad because the actual periodic table is 12.0115 for an atomic mass unit, so pretty close. So that's how you figure out the atomic mass unit for an atom on the periodic table. You have to do what's called a weighted average and not a straight average. Okay. Another example of a straight average would be kind of like what you do with test grades. Let's say that you got like a 90% on one test, and you got a 95% on the other, and you got 100% on the other. If you were going to take the straight average of those numbers, you're going to end up with a percentage of 95%, which is what you would expect. Each one has the same value for your test average for that course, for that grade. If it's a weighted average, it's kind of like more like final exams, where the first marking period is worth, like 40% of your grade. The other one is your other marking period is 40%, and then your final exam is worth 20% of your grade. That's definitely not a weighted average. You know that your marking period 1 and your marking period 2 equate to 80% of your average, while just that final exam is 20%. So that's more of a weighted average. Okay? And this, again, is how you calculate what a weighted average is. So I hope that helped you understand what the difference is, or what really is an isotope and how they actually calculate the average atomic mass. All those numbers are on the periodic table. And really the reason why they do that is because they're using a weighted average instead of a straight average. Thank you very much for watching.